Let's look at an example on calculating centripetal force. Suppose that I have a stone, just a little stone there, and I tie it with a string, and I hold it in my hand around here. That's my hand at the center, and I swing the rock, the stone, round and round over my head in a horizontal circle. Okay. Now, in this situation, it actually becomes quite obvious that the force acting on the stone must be along this string. Meaning that it must be pulling towards the center of the circle. Simply because the string is the only thing attached to the rock, so it's the only way that a force can act on the rock. So there's no other way, like there's no force, obviously, in any other direction, whether it's in the forward direction or the outward direction, acting on the stone. Right, so that meaning there's definitely no centrifugal force away from the center, and there is no force in the direction of the motion of the rock. Okay, so the direction of motion of the rock is this way. Let's say it has a certain velocity, maybe 2 meters per second. And suppose that the length of my string is 1 meter. Length of my string is 1 meter. And suppose that the rock has a mass of, let's say 0.01 of a kilogram. Just a very small piece of rock. So we know, therefore, it's quite obvious that there's only this force pulling towards the center of the circle, which we call the centripetal force. Okay, then the question now is, I want to find this force. Now, while we are here, I'll just clarify one practical aspect of this motion. Now, there is still the question. There is still a question that some people may ask: if there is no force along this direction of the velocity, how come the stone, which was at first at rest, how can it start going around in that direction and then go around the circle? And even then, while it is going around a circle, it has friction. As it goes through the air, there is air resistance. Okay, so surely there must be a force that keeps it going in that direction. If not, it will just slow down and stop in that direction, and then the force will just pull it into the center of the circle. And also, there is the question that if I actually do this, if I actually hold this in my hand and swing the rock around, then I'm quite sure that at the point where I hold the string, I have to move my hand, swing my hand around in a small circular motion in order to keep it going. I can't just hold my hand at rest. The string would surely just drop to the ground. So now all these practical questions are perfectly valid, and And it is true, actually, it is true that we need to move our hand around in this little circular motion. And the reason is this. The reason is actually to provide a small amount of force along the direction of the motion. Okay. Now, we have to be careful here. All right, this doesn't mean that we need this force for it to go in a circle. So let's look at this carefully. I need a tiny amount of force in this direction. What is the purpose of this force if not to keep it in this circular motion? Right. The purpose of this force, let's see how this force comes about. By moving my hand around in this tiny circular motion, as the little piece of rock goes around in this bigger circle, I would cause this string to tilt a little bit, like when my hand is there, as the rock moves this way, then the string would be at a slight angle to the actual line from the center of the circle to the rock. And this little angle here gives a force in a slightly tilted direction, and that gives this little component of the force along the velocity, along the motion of the string. Now, and at the same time, of course, it would have this component, this much bigger component towards the center. Now, the purpose of this little component is to overcome friction or air resistance as the rock goes round. Right? It's to overcome whatever little air resistance there is. Okay, so that's the purpose of this little force. Now, this much bigger force there provides the force that keeps it in a circular motion. So therefore, the two components of the force serve a different function. Okay, so we will still say that the force to cause it to go around in a circle is the force that points towards the center. And in an ideal world where there is no friction, no air resistance, then we actually don't need that. All we need is this force perpendicular to the velocity, the motion, and the rock would just keep going round and round without stopping at all. Okay, so let's move on now to calculate for our example. We are just going to neglect this force. I'm just going to neglect that force and neglect the circular motion around here. Okay, and I'm just going to calculate this force, this centripetal force, the main one that pulls towards the center and maintains the circular motion. So let's start. To find the formula of this, to find out the value of this centripetal force, I can use the formula. Now there are a few formula. I'll use mv squared over r because this formula, the values needed for this formula have all been given. Okay, so mass is 0.01. Velocity is 2. And r is 1. So that's 4 times that is 0.04 over Newton. And that's the answer. So we have an answer for the force. Now, while we're here, let's think about the work done. Now, work done. What is the work done when this by the force, by my hand, if you like, when the stone, when I swing this little stone round in a circle? Now suppose that, okay, I've just found the force. Suppose that after a short time, this stone moves from here to, let's say, here. And so let's say this distance that it moves is say 0.7 meter. This distance that it moves. We know how to calculate work done is force times distance. Okay, force times distance. So since the force we have found is 0.04 newtons and the distance in this case is 0.7 meters, we can do this and get an answer. Okay. But that answer would be wrong. That answer would be wrong. The reason is this. If you remember how to calculate the work done, it is not just this formula. There is also the condition that the distance or displacement must be the component of the displacement in the direction of the force. So let's say we have the rock moving in this direction, so we would just use that distance. But if the rock is moving at a slanted direction, we would take the component of that displacement vector along the direction of the force. But in this special case where the displacement is completely at right angles to the force, then it means that the displacement has zero components along the force. So that means that this shouldn't be 0.7, this should be 0. And this means that my answer is 0 joules. The work done on the object moving around in the circle is 0 joules. Okay. Now again, if you want to be very precise, meaning that not very precise, if you want to be more practical and take into account the friction, the air resistance, meaning that I must move my hand around in a small circular motion to give a little force component to keep this rock going against the air resistance. Now if I do that, then I would have a small component of force along the direction of the displacement. Now that tiny force would do work on the stone, and I would use that tiny force in this calculation. Okay. But if I neglect that air resistance, then, or if I consider the centripetal force directed towards the center, then the centripetal force never does any work on the stone that it keeps in circular motion.